Welcome to Ask and Learn.
3 moles of argon gas assumed to be an ideal gas, originally at 1.5 times 10 to the 4 pascals and a volume of 0.028 meter cubed, are first heated and expanded at a constant pressure to a volume of 0.0435 meter cubed. Then heated at a constant volume until the pressure reaches 3.5 times 10 to the 4 pascals, then cooled and compressed at a constant pressure till the volume is again 0.028 meter cubed, finally cooled at a constant volume until the pressure drops to its original value, 1.5 times 10 to the 4 pascals. Draw a PV diagram, calculate total work done by or on the gas, and calculate the net heat exchange for the surroundings. Does it gain or lose heat overall? All right. So let's just write everything down first. So I'm just going to call these pressures P1 and P2. So let's call P1 1.5 times 10 to the 4 pascals. P2 is equal to 3.5. Oh, was it 3.5 or 3? Hope it was 3.5. Okay, great. It was 3.5 times 10 to the 4 pascals. And V2, let's call that one 0.0435 meter cubed. And V1 is 0.028 meter cubed. And I think that's it. Okay, so let's draw the PV diagram. So here's pressure, and then I'm going to put it in units of times 10 to the 4 pascals. And then I'm just not even going to label any of the numbers. If you want, you can label the numbers. So there's your P2 and there's your P1. The P1's less. And then again, I'll just label V1 and V2. And so if you reread it, it says everything's either happening at a constant volume or constant pressure. So this is what the process looks like. Let me label the volume axis. So that's volume and units of meter cubed. Because if you're not actually writing the numbers, it doesn't really matter what you label the axes. But since label V1 and V2 are meter cubed and P1 and P2 are pascals, I'll label them that way. And actually, I'll just take away the times 10 to the 4 to sort of make the notation more consistent. Oops. I'm just going to erase this. Okay, so there's a PV diagram, and our goal is to get the work. So for part A, we want to get the work. And so the work is going to be the total work done. So throughout the whole process, the work done is only done when you change volume. So there's a process work done going from V1 to V2. And I'm going to shade in the area that represents the magnitude of that work with red, and the work associated with going from V2 to V1. And then the work associated with that is the area under the curve, the PV curve, which is that area. And now let's think about the signs. If the volume gets smaller, the work done by the gas is negative, and the work is P delta V, so it's negative. And if the volume's increasing, then it's positive. So V1 to V2 is positive. So the net work is the area of the red part, which is going to be P1 times V2 minus V1, and that's positive. And then the work done during the other volume change happens at pressure V2, and then you're going to go at V2 minus V1. And yeah, okay. So if we simplify that algebraically, we got P1 minus P2 times V2 minus V1. And if we go ahead and plug in numbers, so that's 1.5 minus 3.5. Sorry, that's ugly. Times 10 to the 4 pascals. And then delta V is, yeah. Kind of ran out of room on this line. Delta V is 0.0, or V2 minus V1 is 0.0435 minus 0.028 meter cubed. Okay, so if you take this and plug it into a calculator, you will hopefully get negative 310 joules. So then the question asks, well, what's the heat done during this whole process? I'm going to kind of put B up here. Oh, and I'll box the answer for A. Great. So for part B, to get the heat, you want to always use delta U is equal to Q minus the work done by the gas. If the gas ends at the same spot, the delta U is 0 because the U depends on like the state of the gas, not the process that it has undergone. And so if it starts and ends at the same process, it's going to be at the same temperature. Or another way to think about that is that if the process starts and ends at the same place in the PV diagram, then from PV is nRT, the temperature is going to be the same. And since U just depends on temperature, then delta U has to be 0. So this goes to 0. And then you get Q equals the work done by the gas. And then that's equal to minus 310 joules. And so heat leaves the system during this process.